Hi everyone. Today we're going to go over some of the errors that have been made over the last couple of weeks' work. If you feel that you have cleared up your misconceptions since you've done the assignment, then feel free to fast forward and go on to the sections that you really need. We're going to start with the cognitive assignment for ideal gas laws and kinetic theory. And then I'm going to go over the assignment on kinetic theory for 3.23, I think it was. And then lastly, I will go over oscillations, assignment 4.2, 4.1.2. That's the one. Okay. Anyway, it'll all make sense in a minute. The first question from cognitive that a couple of you got wrong was just understanding what the temperature of an ideal gas is a measure of. Hopefully by now you've cleared up that kinetic energy is related to temperature proportionally, and so therefore temperature of an ideal gas is a measure of the kinetic energy. Remember, kinetic theory is all about describing the behavior in real life using the behavior microscopically that you can't see. And this is a perfect example. Temperature of an ideal gas is a measure of what's going on microscopically in terms of their motion. Now, this is a really common one using ratios. You have two identical boxes, X and Y. They contain the same ideal gas. The mass of gas in box Y is twice that in box X. But the gas in box X is twice the temperature in the gas in box Y. What is the ratio of the gas pressure in X to the gas pressure in Y? Have a go at this question now. The ratio is 1 to 1. If you get that question right, then you can move on. If not, then you have to listen to my boring explanation. Have a go at it before you continue. So, what do we know about box X and box Y? Well, we know that the volumes are the same. As they are identical. We know that the number of moles of box X is twice that in box Y, because the mass of gas in box X is twice that in box. The mass, of gas in box Y is 2 times the mass in box X. Okay, so we're going to write an equation for that. We also see that the gas in box X is at twice the temperature of the gas in box Y. So let's write that as an equation. So what we've got here are just some equations describing what the question or what information the question has given us. So let's have a look at the pressure relationship, because it's asking us about the ratio of pressures. The equation we're using is PV equals nRT. If we make P the subject of the equation, we're left with nRT over V. Now we want the ratio of the two pressures, Px over Py. So we're going to use the relationship nRT over V, X, and nRT over Y. Now we can cancel things out here because we have some constants. R is a constant, so we can get rid of that. And V is a constant, as we've ascertained before. So that leaves things a little bit easier, which leaves us with much simpler nx tx over ny over ty. And now we're going to substitute in these ratios, these relationships that we came up with before. We're going to substitute for y, the y values, and we're going to leave everything in terms of x. Okay, so this is what it looks like with the substituted values. We have Na equals to nx, to ny, equals 2nx. So that's a 2 there now. And we have tx equals 2y. So that actually means that ty is tx over 2. Here we go. And of course, if you look at it now, these two values cancel. So actually we're left with a ratio of 1 to 1. Now, this seems like a really long-winded way of doing it. You might be able to do it an easier way, but this way you can see my thinking and you can apply this idea to much more complex examples. I'll see if I can dig some out for you to practice. So I'm going to be evil now, and I've changed this question so that the boxes are no longer identical, right? They're different sizes. And the mass of gas in box X is twice that in Y. But the gas in box X is 3 times the temperature of the gas in box Y. What is the ratio of the gas pressure in box X to the gas in pressure in box Y if the volume of box X is 2 times the volume in box Y? So have a go at that one now. Okay, so this time you get a ratio of 3px equals 4py. Is that what you got? So this one was a little bit more challenging, but see if you can follow it. If we substitute in our values for nty over x, because remember, we're doing p equals nrt, but the r's cancel. We've substituted our ratio information from here. So the fact that ny equals 2nx, the fact that ty equals tx over 3, and the fact that vy equals vx over 2. And we can cancel all these out now. We can cancel the nx's, the tx's, and the vx's. And we're left with the coefficients. And so now it's just maths. 1 over 2/3 divided by a half gives us 1 over 4/3, and that gives us 4/3. So this is a descriptive question. A sample of an ideal gas contained in a cylinder, which is kept closed by a piston. The volume of the gas is suddenly increased. What will happen to the average kinetic energy and to the frequency of collisions? Now, this is a sneaky way of asking you, what will happen to the temperature? And what will happen to the pressure? Because we know that kinetic energy is proportional to temperature, and frequency of collisions is a measure of the pressure. So if we think about our relationship, PV equals nRT, what we've done here is we have changed the volume. The volume is increased. So if you increase the volume, have a think about the consequences it will have on pressure and temperature. Right, it's important to go over these because none of you got these right. The average translational kinetic energy at temperature T of helium, molar mass 4G, is K. The average transitional kinetic energy at the same temperature would be which of the following? And the next question is similar. The atomic mass number of helium is 4 and that of neon is 20. When both gases are at the same temperature, the ratio of the average speeds of helium to neon will be. So have a go at that question now. See if you can remember what your thinking was. Well, firstly, let me give you the equation you're using. So we're using kinetic energy here equals 3 over 2 molar gas constant R over Avogadro's constant times temperature. These two are constants. Now what I've done is given you the expanded form of kinetic energy, which is a half mv squared. So that's the relationship we're using. Now, if I rearrange this to look at the relationship between kinetic energy, Ke, kinetic energy, over temperature, is always going to give you a constant value. This is not going to change. So it doesn't matter if it's the kinetic energy of neon or if it's the kinetic energy of helium, that ratio of EK over T is always going to be the same regardless. Now, if we change the mass, we're changing the kinetic energy. But that's beside the point, because what they're telling you in this question is that the temperature is the same. So if I do something now to change the temperature of a gas, the kinetic energy has to change accordingly in order to keep this constant the same. So for question 1, the answer is C. The kinetic energy has got to be the same if the temperature is the same, because the value of EK over T has to be constant. So for helium, temperature is the same, then kinetic energy must be the same. Neon, if the temperature is the same as for helium, the kinetic energy must be the same. I hope that makes sense. The second question is a little bit more complicated. The atomic mass of helium, same as neon, okay, we're using the same ratios. When both gases are at the same temperature, like here, the ratio of the average speeds will be, now, why would the speeds be different? Because EK equals a half mv squared. Now, if the kinetic energy of both has to be the same, but the mass of them is different, then the speed has to change to compensate for it. See if you can figure out what the compensatory value would be. Okay, so to recap, the kinetic energy of both of these is the same. Kinetic energy of the helium is equal to the kinetic energy of the neon. So ultimately, our ratio must be 1 to 1. Now, from the question, we can see that the mass of neon is 5 times the mass of helium. And you can see that from the numbers. Helium has a mass number of 4 and neon has a mass number of 20. So that's how we could represent that as an equation. The velocity ratio, we don't know what it is. So I'm leaving it like an X. The velocity of the neon is going to be X times the velocity of the helium. And we'll plug that into our main equation here, which should give us ultimately 1 to 1. The ratio of the kinetic energy of helium over the kinetic energy of neon. Now what I'm going to do is substitute these values in. And here you go. I've substituted all my values, so I have the kinetic energy for both in terms of helium. So here we can see a half mhbh squared over a half 5mh times xv squared. Now, we know that all of this will give you 1. So this 5 multiplied by this squared should give you 1. So we want x squared to cancel the 5. So let me make some space. Okay, so let's have a look at that. 5 times x squared gives us 1. So that means that x is 1 divided by 5, and then the square root of 1 over 5, right? So our answer for x is 1 over square root of 5. That funny noise was my cat, by the way. It was not me. So let's go back to the question, because we've done this a little bit more like maybe messily than we should have, because I've got everything in terms of the mass of neon, right? So basically, let's look at our answers. The atomic mass number of helium is 4, that of neon is 20. When both at the same temperature, the ratio of the average speed of helium to neon. So now what we can see is that the answer is B. I'd had it, it's 1 over square root of 5 if you do the average speed of neon in terms of helium. But the other way around now would be square root of 5. I hope that makes sense. If that doesn't make sense, please let me know. And you can do that by using the comments in Classroom, an email, or Carrier Pigeon, whatever you fancy. All right, but please let me know if you don't understand. And now to the last question, which is actually quite similar because it's this idea of constants in proportional relationships. This is now 4.1 oscillations. Make a copy of 4.6. Well, basically, we're looking at this equation. And suppose that the graph you've drawn represents a graph of simple harmonic motion, the relationship of a mass oscillating on the end of a spring with a force constant of K. You add 2 lines to represent 0.5. So basically the same mass oscillating, but with half the mass. And then a mass m, but a force constant of 0.5 K. So let me write down all the relevant relationships. Okay, so let's see if we can make some sense of this. The defining equation for simple harmonic motion is acceleration is proportional to minus displacement. We're going to ignore the minus for now because that's basically showing you the direction of increase, right, for now. So let's just leave that for a second. If I make this into a linear equation, like get rid of this proportionality, then I take the x over to this side, and I have acceleration over displacement equals a constant. Now see if I can find that constant value. I've got 2 relationships to play with. I know that force equals mass times acceleration. But this is a spring, so I also know that force equals the spring constant times displacement. Well, it's the same force, right? So I can substitute those values in to give me mass times acceleration equals kx. If I bring the x over to this side, I have a over x equals k over m. Does this look familiar? I hope so, because if now I multiply this by minus both of them, I end up with the same relationship I had before, right? I can see that a over x equals k, a constant, but now I know what that constant value is. Now, what does this k actually mean? Any ideas? A over x, acceleration over displacement, is going to give me the slope, right? So k over m, which is equivalent to that constant, is going to give me the slope. So now let's see what these questions, how can we solve these questions? If now I make the mass half, I reduce the mass by half, what effect will this have on the slope? Any ideas? It should make the slope much bigger. I'm going to make a mess of this. Yes, I've made a mess of it. That's better. Okay, so I'm going to have a much higher slope. And then for part B, the mass m on the spring with a force constant of a half k. What will happen to the slope if I make k, or I reduce its value by a half? It's going to make the slope half as big. There we go. Okay, it's not a common question and it is tricky, but I hope you get it now. Right, I think that's it now. What I need from you in the comment section or in private, can you please let me know how you feel about these questions now? I know I made it optional in the previous question, but I think I want some feedback from you guys. So let me know how you feel about these questions now, if you feel that you can do them.